Hello, I'm Nikias Klohr, Head of R&D here at Result, and today I would like to walk you through the UHF timing basics. Actually, many or most of you probably know that all the big scale marathons worldwide are now done with UHF transponders, and the things I will be going to talk about today do not only apply to our UHF timing systems, they apply to UHF timing in general. Obviously, some of the details are more specific about how our system operates, but overall it should be a basic introduction on how the technology we all use actually works. So let's get started. Let's think of a basic setup where you have a decoder box next to your track, and you have a floor antenna on the ground which has several elements which are connected to your decoder with several cables. The first very basic thing that you need to know is that there is only one antenna element on at any given time. Actually, the decoder box switches through the antenna elements all the time. So it's not all antennas on at any time, it's only one single antenna which is used at every single time. We call that multiplexing. Multiplexing means that actually the receiver in this box only has one receiver channel and there's only one transmitter in the box. And this one transmitter is using all the different antennas to talk to the transponder, but it's only using one antenna at a time. Obviously, the time that a transponder spends in reach of the antenna is limited. So the multiplexing rate at which the transponder can be detected because the antennas are switched through is important. It's important to have a high multiplexing rate. So now let's concentrate on one single antenna. Typically, the one single antenna readout period is only a few milliseconds, thousandths of a second. What's actually happening there? So what happens is that the decoder will power the antenna on our carrier frequency, which is normally around 866 MHz in Europe and about around 915 MHz everywhere else. And it will give power to our transponder. Now, the important thing in passive UHF transponders is that they are passive. They don't have a battery. So they need to get their power out of the RF carrier frequency, which is transmitted on that antenna. So typically what happens, if you look at the time frame, is that the decoder will power up one single antenna like this, give a certain amount of time, which is a few hundred microseconds, so a few hundred millionths of a second, to actually apply power to the chip, which is in reach. And then it will start modulating that signal to transmit data to the chip. And then the chip will try to answer by short-circuiting its antenna or not. So actually what the chip is doing, it is reflecting the power which is coming from the antenna going to the chip. There is a reflection going on the chip's antenna, which is actually modulated by short-circuiting the chip's antenna or not short-circuiting the antenna. What's important is that if you look this as a power diagram, it's power over time, that the chip signal is actually very, very small, something like that, compared to the power which is transmitted by the decoder. This means that if you look at this system where one single antenna is the transmitting antenna and at the same time the receiving antenna, the signal which needs to be received by the decoder is extremely small compared to the signal that we send to the chip. And this is where the antenna quality comes into place. Because if you look at antenna basics, if you send a signal to this antenna, the antenna will try to get as most of this signal radiated out into space, but some of it will not be radiated and will directly be reflected by the antenna itself. And as some of you may know, we have a return loss warning on our system, which actually refers to that specific problem. If you detune, or if you have a bad antenna here, you have a bad return loss value on that antenna, meaning that this antenna reflects a lot of the power that it's seeing from the decoder, making it impossible to detect the actual response from the transponder. Bad return loss values normally come from detuning of the antenna, which typically happens by, for example, putting something on the antenna. So if you see a return loss warning on the decoder, make sure you have nothing on the antenna, or maybe you don't have it folded together. Disconnect pieces which are not folded together, which are folded together. Make sure that the antenna works as it should be, so that we have a good chance of actually detecting the transponder's response. So actually it gets a little bit more complicated than this. If you look at this, here the decoder sends some data out, and obviously all transponders within reach of that single antenna will get this command, what we call it, and will start a response. Now what happens is there is a random time where the first transponder starts to respond, and then at a certain other random time the next transponder starts to respond, and another third time, or fourth or fifth or whatever time, the next transponder starts to respond. And what the transponder actually does in its response is it gives the decoder a random number under which it can now be addressed. So in a next step, the decoder again sends data to the first chip, okay, let's say 1, 2, 3, and it asks the first chip of the 3 to send its EPC data, where at the end the bit number is coded into. So here you get another response of the first chip, so this would be the actual data of the first chip. Then the decoder asks the second chip to respond, and you get the second chip, and then it asks the third chip, and you get the response of the third chip, and then the power is dialed down, and all this happens for every single antenna about 40 times per second. Now, one process like this leads to one hit that you can see in the decoder's data at the end. And now if you imagine what's actually going on here, multiplexing through all these antennas 40 times per second, querying for chips in reach and then acknowledging each single chip, there's actually quite a lot going on at all times here. It's also important to note that this time, how long it takes to actually go through all chips which are in reach of an antenna, depends on how many chips are in reach on that antenna. So it does make a difference for all UHF systems how many transponders are in reach of an antenna. This will be of importance if you discuss different setups of antennas, where we believe that the floor antenna is actually the best antenna you can use, because it reduces the amount of chips seen by any single antenna, because actually the floor antenna is looking upwards to the sky, giving you the least amount of chips at any given time within the reach of the antenna. Okay, so now you may ask yourself, how does the detection actually work? If you look at the data, you will normally see if a transponder passes a antenna mat, a race resultant antenna mat, you will normally see somewhere, I would say, between, let's say, 20 and 100 hits. We now learn that every single process like this is actually only one hit. Okay, so if a chip goes over the antenna, let's say here, it is actually detected by this antenna, and this antenna in most cases. And the hits are put into memory in this decoder, and the decoder is looking for the highest signal strength. We will do a separate video on how the detection algorithm actually works. You will find it linked below. But the important thing is that normally the transponder is received over quite a long distance across the mat. So we have a high chance of detecting it. The critical thing is to pick the right time, because at the end we're doing timekeeping here and not only detecting transponders. And for that, the most critical thing again is the multiplexing rate. Because let's say that the multiplexing rate would be very low and every antenna would only be on once per second. You might pick up the transponder, which would be okay, but it would be a completely different time. So, some more specifics about the race results system. Some of you probably know that you can get our standard 4.8 meter antenna, and we also offer extensions for that. The 6 meter antenna is actually the same, just with 2 blind elements on both sides, but the 8 meter antenna adds blind elements in the middle. Obviously, this is not to scale, but you can think of it of taking out this antenna, taking out this antenna, taking out this antenna. So we only have every second antenna actually detecting anything, because those are blind elements. So why does this still work? Actually, it only works for certain transponder types. So if you look at the cross-section of this antenna here, let's say we're looking from down here, okay? You have the antenna on the street with all the different elements, and let's say like that, and actually with the antenna, this one is empty, and this one is empty, and this one is empty. You have an antenna here and you have an antenna here. The field over the antenna will open up like this. Okay? So there is a blind spot down here, which you should not go through with a transponder because you won't detect it. But up here, those 2 antenna elements are enough, more than enough, to detect all transponders. So if you insert blind elements, you can, without any problem, use the antenna with transponders worn at the bib level, but you can't use it with transponders worn at the ankle, because the ankle would go through down here and you would not detect it. So the next thing that many of you do is you use more than one UHF timing system or one of our decoders at one timing location. So typical setups would be something like this, where you have a decoder on this side, obviously not to scale, and another decoder on this side, and you put one antenna like this, and you put another antenna like this, connected to your decoder, and you have your antenna elements here. This is typically done if your antenna is not long enough, obviously. What then is also added is you add another 2 decoders with exactly the same setup, like this. So this is actually already the most drastic way of doing this. Some of you may also only use half of the setup if this is only your width of your track. But let's discuss this here briefly. What's actually happening? So one important thing is that if you look at this up here, one decoder talks to a chip answers, it's asked again, answers with its EPC. It's very important that this process does only work from the chip's view for one decoder at a time. If a chip were to be addressed by 2 decoders at the same time, it would not know what to do. It's basically like you trying to have 2 phone calls at the same time. It does not work. So it's important that you know that a chip can, no matter what, only talk to one decoder box at a time. So if you look at situations like this here in the middle, you can immediately identify that there might be a problem. Because with the multiplexing, this decoder is going through its antennas here 40 times per second, and this decoder is going through its antennas 40 times per second. And once in a while, those two antennas in the middle will be on at the same time. It can just happen. It's pure statistics of how many times it happens. So if those two antennas are on at the same time, and if you look at the pattern of the antenna, you might run into a situation where a chip which is in the middle over those two antennas, or even not even in the middle, slightly offset, is addressed by two decoders at the time. Actually, that chip will suffer significantly in detection rates. You might be lucky and still get it, but it's not recommended to do it that way. Actually, in a setup like this, it is strongly recommended to insert a blind element here so that you don't run into a situation where a chip has to talk to two decoders at the same time. Basically, you create a situation like this. It's still not perfect, but it's much better than having two decoders right next to each other. The same applies for this here. If you look at the distance from here to here, actually let's do that in red again. At this distance, obviously the chip can be detected by both systems at the same time because you have this opening of the field which also goes in this direction. So it's important not to put the decoders next to each other. Actually, we say that you should have at least 3 meters of distance between the first and the second line. No matter if it's a 4 decoder system setup or only 2 decoders, you should always have at least 3 meters between the two systems, so that you don't run into the problem that the chip needs to be detected by both decoders at the same time. So now for our EU customers, there is another thing which is important. Unfortunately, in the EU, UHF works on a very small spectrum. We only have 4 different frequencies which are quite close to each other, and which is not a problem anywhere else in the world. It's just in the EU. So our EU decoders have a setting where you can set the decoder to A and B frequency. A and B frequency meaning that the A frequency switches back and forth between two of the two frequencies, and the B frequency switches back and forth on the two frequencies. And that helps to get the interference between two decoders down. So in a setup like this, you start with one decoder, you set it, let's say this one here to A. You set obviously this one here to B, because they are close to each other in this direction. This would also be your normal setup if you just have 2 decoders, A and B. Now this decoder and this decoder should be on different frequencies, so you set this one here on B. Oh, let's do it nicely. And this here on A. So this would be your typical frequency setup in Europe. As I said, in other countries, you don't have to care about that. Doesn't matter. Okay. Now that we've talked about multiple decoders, actually, why do we do this with backup lines anyway? Some of you or most of you might know that we normally say you should have 1 line of redundancy. You should either have 2 transponders on your bib or 2 lines on the ground. Actually, the question is, why do we recommend that? Actually, it's not because we don't trust our chips. It's not because chips break or anything. It is actually because of a very simple reason. The main problem for not detecting UHF transponders is the participant blocking his own transponder with his own arm when stopping or starting his wristwatch. Okay? So what normally happens is that if you have 2 transponders, the participant only manages to block one of the 2 transponders and the other one will work. Obviously, the UHF does not go through the human body, so it does not go through your arm. And if you put your arm on that transponder, it will not detect. So again, normally if you start and stop your wristwatch and you have two transponders, you will only be able to block one of them, either doing it this way or this way, but not both at the same time. So in that case, if you have two transponders, one line is enough. Now obviously there is some economics in play here, because two transponders cost more than one transponder, and for larger races you would want to have a backup system anyway. That's not because of detection rates, it's actually because of hardware redundancy. Probably many of you have seen cases like this. Things just go wrong. Things happen. People step on systems. People spill their Coke into the system. Things like that can happen. And at the end, you are much safer on large-scale races if you have two systems. So we recommend, or I personally recommend, if you have more than 1,000 participants, go for two and use one tag. With one tag, you still have the problem that you block the transponder at the finish line or at the start, with starting and stopping your wristwatch. But normally you have your arm down or up, depending on where you do it, once you get to the second system. So the chance of actually blocking a transponder by stopping a wristwatch on both systems with 3 meter distance obviously is much lower. Okay, so now the last bullet point for today's presentation here is about side antennas. I know some of you use side antennas, some of you don't. We normally don't recommend them because we believe that for most applications the floor antenna is the best option. Let's go into some details about this. Actually, there is something called the free space loss, which is the FSPL, which you can look up on Wikipedia. Actually, it is a very basic formula for calculating signal power over distance. And this free space loss has one important factor. Actually, it says that the power which is received over distance goes to 1 over the distance squared. This means that if you double the distance, you only get 1/4 of the power out of it. Now obviously, talking about this up here again, we need to power the chip. So enough power needs to go to the chip. And don't get confused with free space and free air measurements where you can detect chips in 20, 30, 40 meters away, because in our application the chip is close to the body. And the body is detuning the antenna, and the body is taking a lot of the RF power which actually should power the chip and heating up the body. So there is a huge difference between a transponder in free air and a transponder on the body. So in passive UHF timing, it's always about getting enough power to the transponder. And if you look at this, it's important that the distance between the transponder and the antenna is minimized. We believe that the floor antenna is actually the way of getting the lowest distance between chip and antenna. If you think about it, if you would use side antennas or overhead antennas, you always have a larger distance between the antenna and the chip. Let's say overhead antennas, you could argue you could put them as low as the distance between the chip and the floor, but actually that's not true, because you need to make way for emergency vehicles, and normally a truss, overhead truss, will not be as low above the head of the transponder, or the participant, as the distance between the bib and the floor. So the minimum distance between chip and antenna can be achieved with floor antennas. If you set up side antennas, let's do this here. Let's say we have a side antenna sitting here and sitting here, looking across the track. Obviously, the largest distance you can get is to the center, and this distance is significantly longer than the distance from the floor to your transponder. There are applications where this still makes sense, especially when the chip is not on the body. So for example, for mountain biking, road race cycling, things like that, where you mount the transponder on a bike and you can have it basically hang in free air. Side antennas might be a good choice. There's one more thing which makes it a little bit difficult. Actually, UHF does not travel through the human body very well. So as soon as you have a situation where more than one participant comes through, especially if you have a larger bunch of participants, with side antennas, you will run into difficulties. You will, at the very least, get lower detection rates and so lower precision, but you even might miss a participant. So for situations where you know that you have large bunches of people coming through, we do not recommend side antennas. There's another thing. Actually, if you look at it from a bird's view, top view, the side antenna field goes out like this again, like same thing like here. So the precision that you can achieve with this kind of setup is lower the farther away the transponder is from the antenna. This can be compensated by connecting two side antennas on both sides to the same decoder box, which is always recommended, because if you connect them to two different decoders, they will block each other out and you will have very bad detection rates. So always connect setups like this to the same decoder box on one side of the street. But this again leads to the problem that you somehow need to get your cable over there. And actually that cable also introduces new losses, which can deteriorate your signal on this side significantly. So looking at the detection again, you have one coming from this side, one coming from this side, and your worst detection precision will actually be in the middle of the road, where probably your winner will go through. So setups like this are used by some people, and we have customers using them quite successfully. But the sum of all of this makes it the not so much recommended version compared to floor antennas whenever you can use floor antennas. Obviously, floor antennas sometimes can't be used, especially on very uneven ground, or if it's a tripping hazard or a falling hazard for high-speed cycling especially. One more thing about the side antenna. I already addressed that you should not use side antennas with multiple decoders. Actually, if you would connect this side antenna to one decoder on this side and this side antenna on one decoder on this side, they would basically cancel each other out. This would not work very well, because they would be firing those side antennas at each other and they would not be seeing a lot of chips. So make sure that if you have more than one decoder with side antennas, that you set the side antennas in a way that they don't see each other. So basically, if you have a second decoder and a side antenna situation like this, you set it up down the road and maybe even looking in that direction. Something like that. This would be a second decoder and not this. One final note about this. We believe that the floor antenna looking upwards has another great advantage. As I already said at the beginning of this video, the floor antenna looking upwards, looking in the sky, only addresses chips which are directly above the antenna. If you think about it, in a situation like this here, free space chips in free air will also be detected somewhere over here or somewhere over here next to the track. So especially at a finish line situation where participants finish and then come through and stick around to watch the others, they will be detected all the times. Now you might say this is not a big problem because you can filter that out with your software. Every good timing software should be able to do that without a big problem. But if you think about this process going on here, it actually reduces the chance to get a transponder that you want. Because if the system always has to talk to transponders which are behind the finish line, let's say like this somewhere back here, This antenna has to address all of them. It does not know where this transponder is. It does not know if it's here or here. So it has to go through all of this for every single transponder that is next to the track and not on your track. At the end, if you're lucky, it won't really make a big difference because you will still get the transponder here, but you might not have the same kind of detection rate and you will never have the same kind of precision because you will not detect it as often and you will not be able to get the same detection algorithm quality as if it was only this single transponder. So keep in mind that for the decoder, it does make a difference how many transponders are in reach of the antenna, even if you can filter it out of your antenna software. Sorry. So, I know this is a very technical video today. Actually, we did this because on our user conferences and distributors conferences in the last month, I had lots of discussion with people and they were asking for more technical stuff. So this is actually something you would normally learn on our user meetings. If you're interested in more things like that, please comment in this video and tell us about it. We can do more technical videos explaining more of how this stuff actually works. If not, then we will stop doing videos like that again and stick to the old kind of videos that we did. So, thanks for watching.